Dear students, welcome to third class of chapter 2, solar radiation. I would like to tell a very small story which may inspire you. It is a wild ass and the lion. A wild ass and a lion entered into an alliance so that they might capture the animals of the forest with greater ease. The wild ass and the lion. The lion agreed to assist the wild ass with his strength, while the wild ass gave the lion the benefit of his greater speed. Greater speed, the wild ass. The strength, lion. Okay, they joined together for what? To capture the forest animals. Okay, when they had taken as many animals as their necessities required, the lion undertook to distribute the prey. That means the lion, having all the whatever they had taken together, kept in front of it, and it divided it into three shares, three parts. Okay, what all they two together captured. The lion said, I will take the first share. Okay, the wild ass agreed. The second share was given by lion to the wild ass. Hey, the third share will go to me automatically, said the lion, saying that because I am king, you willingly give it to me, otherwise I just take it. What, you just cannot do anything. I am mighty, I am very strengthy and king of the forest. So the wild ass set off as fast as it can. The meaning or the moral of the story is, might makes right. Might makes right. Now, so let us go into our class. In today's class, we are going to discuss two important subheadings which are very interesting, and both these two subheadings have potential to come to appear in the midterm exam and theory final exam. These two are: one, factors affecting the distribution of solar radiation within the plant canopy, and physiological responses of crop plants to different bands of incident radiation. Now, so what are the factors affecting the distribution of solar radiation? Just what we discussed in the last class. If we try to recapitulate the factors affecting the solar radiation received on the Earth's surface. Factors affecting the solar radiation received on the Earth. Last class we discussed the major factors are astronomical factors and geographical factors. In the astronomical factors, solar output, distance between the Earth and the Sun, and altitude of the Sun. In the geographical factors, four are there: effect of atmosphere, effect of latitude, effect of aspect and altitude, and length of the day. Now, in this class, we are discussing factors affecting the distribution of solar radiation within the plant canopy. If you just go to your farm, stand in front of a crop, so what are the factors that are affecting the distribution of solar radiant energy falling on that? There are altogether 8 points. I just to try to explain in a very simple way. The first factor is type of plants. The leaves of cereal crops like paddy, wheat, etc. have a transmissivity from 5 to 10%. The broad leaves of evergreen plants have lower value of 2 to 8%, whereas aquatic plants have 4 to 8% of transmissivity. Transmissivity changes with the age of a leaf. So that means different types of plants have different transmissivity. For example, paddy, wheat, cereals 5 to 10, evergreen plants 2 to 8. In case of aquatic plants, it is 4 to 8. So, type of plants means cereal crops, evergreen plants, aquatic plants, because of their type, because of transmissivity, affect the distribution of solar radiation among them. Now, age of the leaves. Second factor is age of the leaves. The transmissivity of younger leaves is more as compared to older leaves. It is a natural scientific principle. The transmissivity of younger leaves is more compared to older leaves. The chlorophyll content. As the chlorophyll content increases, the values of transmissivity decreases. That means more the chlorophyll content, lesser the transmissivity, and vice versa. The fourth factor is arrangement of the leaves. The relative light interception by horizontal and erect foliage is 1:0.44. The relative light intercepted by horizontal leaves and erect foliage is 1:0.44. When the leaf area index is 1, the light transmissivity of more upright leaves is 74% as against 50% for horizontal leaves. Okay, so the arrangement of the leaves play an important role. Horizontal leaves, erect leaves. Horizontal leaves and erect leaves light interception is 1:0.44. When the leaf area index is 1, the upright leaves, the transmissivity value is 74%, just to 50% for horizontal leaves. Now, the fifth point is the angle of the leaves. In full sunlight, the optimum inclination for efficient light use is 81%. At full sunlight, a leaf placed at the optimum inclination is 4 to 5% times as efficient as in using the light as a horizontal leaf. A full sunlight, a leaf placed at the optimum inclination is 4 to 5 times as efficient in using the light as horizontal leaf. The ideal arrangement of leaves shall be that the lowest 13% of the leaves lay at angles between 0 and 30 to the horizontal, that the adjoining 37% of the leaves lay at 30 to 60 degrees and the upper 50% of the leaves lay at 60 to 90 degrees. This is the ideal arrangement for angle of the leaves for distribution of solar radiation within their canopies. The next one is the plant density. In case of sparse crop stands, not only the upper parts but also lower parts play an important role with reference to distribution of solar radiation. In case of very sparse, very thin otherwise crop stands, not only the percent of light transmissivity is more, but it is also variable within the time of the day. It is minimum at noon and maximum during both morning and evening. In dense crop canopies, the light transmissivity is less. The next factor is plant height. When the plant height increases, the transmissivity of light by the canopy decreases. The eighth one is angle of the sun. The highest radiation penetration occurs at noon. Penetration. Okay. Similarly, relatively high radiation penetration also occurs both in the morning as well as before the sunset due to high proportion of diffuse light. So, angle of the sun, the highest radiation penetration occurs at the noon. Relatively high, not highest, relatively high radiation penetration occurs both in the morning as well as before the sunset due to high proportion of diffuse light. So, these are the basic factors affecting the distribution of solar radiation within the plant canopy. These are once again for your benefit from your examination point of view. This is the most important question both for midterm and theory final. So you should write all these 8 points: type of plants, age of the leaves, chlorophyll content, arrangement of the leaves, angle of the leaves, plant density, plant height, angle of the sun. Now, so let us move on to second subtopic of today's class, that is physiological responses of plants to different bands of incident radiation. The Dutch Committee on Plant Irradiation has divided the solar spectrum into 8 bands. In the first class of solar radiation, I told 3 bands: UV rays, light rays, and infrared rays. Now, the Dutch Committee on Plant Irradiation has divided these 3 bands into 8 bands, and they have done research, and based on their research, the physiological response of plants to incident radiation is as follows. Once again, I would like to impress upon you the 3 bands are divided into 8 bands. Each band has its own physiological effect. What is it? Band 1, it is the infrared more than 1 microns. It is absorbed by water in tissues, and as far as its physiological effect is concerned, it is converted into heat. This has no specific effects on photochemical and biochemical processes. Band 1, more than 1 microns, absorbed by water, converted into heat. Now, the second band is 1 to 0.7 microns. It is slightly absorbed by the water. As far as its physiological effect is concerned, it stimulates elongation in plants. This bit will come. Specific elongation effects in the plants is caused by band 2, 0.1 to 0.7 microns. The third band is 0.7 to 0.61 microns, that is falling under the light. Light is from 0.4 to 0.7 microns. So, 0.1 to 0.7 is the second band which has got specific elongation effect. This bit will come in midterm, this bit will come in your theory final exam. Please note. Now, the third band is 0.7 to 0.61 micron. It has a very strong absorption by chlorophylls. As far as its physiological effect is concerned, large effect on photosynthesis and photoperiodism. Then the fourth band is 0.610 to 0.510. It is somewhat less absorbed as far as its physiological effect is concerned. Small effect on photosynthesis and a small morphogenic effect. The fifth band ranges from 0.510 to 0.4, very strong by chlorophylls and carotenoids. The physiological effect is large effect on photosynthesis and large morphogenic effect. Morphogenically, there is effect by this fifth band 0.51 to 0.4. The sixth band is 0.4 microns to 0.315. By chlorophyll and protoplasm, it is absorbed. Small effect on photosynthesis. It produces fluorescence in plants. This bit will come in midterm and theory final exam. Please note 0.4 to 0.315. It is having small effect on photosynthesis. However, it produces fluorescence effect in plants. Now, the seventh band is 0.315 to 0.28. It is absorbed by protoplasm. It has a significant germicidal action, large morphogenic effect, and large effect on physiological processes. And the eighth band is less than 0.280. It is absorbed by protoplasm. It has a large germicidal effect. It has lethal effects when it is falling in large doses. Now, to sum up the physiological response of plants to different bands of incident radiation, as I said, sun's radiant energy comes in different bands. Basically, we tried in the first class to understand that the solar spectrum is divided into three bands: UV, light and infrared. The Dutch Committee on Irradiation has divided the solar spectrum into 8 bands, and they have done a lot of research on the physiological response of these bands on croplands. Now, the first 2 bands, according to them, fall under the infrared. The third, fourth, fifth fall under the light part. The sixth, seventh and eighth falls under the UV part. Please note that the sixth, seventh and eighth, which are falling under UV part, have germicidal effects. They have little or small effect on photosynthesis. They have germicidal action. What is really useful are third, fourth and fifth with reference to photosynthesis and photoperiodism and photomorphogenic effect. However, the infrared part, more than 1 microns, has thermal effects, or it is converted into heat, which is very essential for the crop plants. Most important is 1 to 0.7 micron. It has a stimulation effect or specific elongation effect on the crop plants. That means whenever a crop is not growing, when you allow that crop to say 1 to 0.7 micron, it gets stimulation. It elongates, the crop elongates. Okay, so this is what in today's class we discussed. Factors affecting the distribution of solar radiation within the plant canopy and physiological responses of plants to different bands of incident radiation. Please note that in the last part, we discussed factors affecting the solar radiation received on the Earth's surface. How from the sun's rays are reaching, what are the factors? There we discuss astronomical factors and geographical factors. But in this class we discussed factors affecting the distribution of solar radiation within the plant canopy. When you go to a plant, when you see a crop, what are the factors that are affecting? And finally, almost at the research level, we also try to understand in this class the physiological responses of plants to different bands of incident radiation. Means when you are standing in front of a crop, different bands of radiant energy is falling, and we tried to understand them in 8 sub-bands. First 2 bands are infrared, 3rd, 4th, 5th are the light bands, 6th, 7th, 8th are the UV part. So UV part has germicidal effects, or they have some sort of morphogenic effect with reference to large negative way, but morphogenic effect positive way. Effect on photosynthesis is by light part, 2nd, 3rd and 4th band. Thank you very much. We meet in our next class.